Hello my friends, it's me once again, from Einstein classes. In previous sessions we understood the concept of force and Newton's second law. In this session we will discuss about the force weight, normal reaction, and weightlessness. First of all, look this video. NASA flight engineer Cady Coleman shows you some experiment from space laboratory and you can feel about weightlessness.
Hello, Katie.
Hello.
This is so cool, isn't it? Hey, Katie, I want
welcome
to ask you
aboard
a
the space
question.
station.
This is Leah. Look at this. Wow. Are you going to be okay, or? There's a delay, too, so we got to take that into consideration. Katie, can you hear me?
You know, we Yes, I can hear you.
Yes.
I want to show you why we do these experiments, and that is because this is a bag of water, okay? And I'm squeezing. Let's see. So it's a brand new bag of water, and so my straw was a little crimped there. And I'm going to come a little closer, and you can see this giant blob of water. And we're getting to see in space, what do liquids really, really want to do?
Wow. That is amazing. That is amazing.
So I'm curious, because I know you have kids at home. How do you stay close to your kids?
Oh, wow.
Amazing.
Yeah.
I'm just curious how you stay close to your kids while you're in space.
Well, one of the ways that we stay close is I try to keep him really interested in what I'm doing, and I'm shaking up our fluids experiment so you can kind of see, you know, what a real experiment looks like, and not just playing with our water drops, but understanding how fluids behave in space. Well, it has to do with everything we do at home. And everything that we wear, everything that is in our house that is made with a process of something flowing through a pipe, we need to understand what liquids do. And this experiment actually shows us how to design fuel tanks for satellites. And you think, well, gee, why would I care? Everybody uses a cell phone, electronic devices, communication, military defense, you name it. And it all comes from things like this. When we talk about trying to keep my son interested, another way I do that is actually to bring one of his things with me up to space. He's a big fan, and so am I, of Calvin and Hobbes. And so I've brought a little Hobbes up in space with me, and I bring Hobbes to do experiments, and I take pictures and send him down to the ground so he understands what I'm doing every day. And I did that while I was training for this mission as well.
What research are you doing in space that you're most excited about?
On a day-to-day basis, I love to do the things that I actually get to touch and move, like the experiment that you saw with the bubbles just now. But some of them aren't as tangible. We're doing some research in osteoporosis, which I think is fascinating and valuable. Basically, I'm an experiment, and because we lose bone mass up here, because we don't walk around on our legs, we lose bone at about 10 times the rate of a 70-year-old osteoporotic woman. And so, because I don't have some of the potential complications that somebody who's 70 might, I'm sort of a clean medical specimen to do some experiments. And so I'm taking some of those drugs, and we're looking at how my bone mass is changing, and we looked at it before I left, while I'm up here, and also when I get home, and it'll help us understand a lot about how osteoporosis, the mechanism of osteoporosis, which certainly affects millions of people down on the earth.
Really amazing. This is the weightlessness or zero gravity. Thank you NASA. In first few sessions of laws of motion, we understood the lifting of space shuttle and rocket. Now we will discuss about the force of gravity and normal reaction to understand weightlessness. The force of gravity on a body P by another body Q will arise due to gravitational interaction between them. You are a body P and the body Q is Earth. The Earth is attracting you towards the center of Earth by a force which is known as force of gravity or weight of body. In free body diagram, the direction of weight will be shown vertical downward and its magnitude is mg, where m is the mass of body and g is the acceleration due to gravity or free fall acceleration, which is same for every body if the body is at the same distance from Earth. Normal reaction. Normal reaction is a pushing force. It is a contact force. This force will arise at the point of contacts of two bodies when two bodies will push each other. The direction of this force along the common normal at the point of contact and along the direction of push on a body by another body. Take an example, you are standing on a floor. You are pushing the floor downward and floor is pushing you upward. Hence normal reaction acting on you vertical upward if we treat you as the system. But if we take the floor as system, then the normal reaction will act vertical downward on the floor. Take another example, a block is placed on a table and calculate normal reaction. Now we calculate normal reaction acting on the block. You can see, first of all, draw free body diagram of block. Apply Newton's second law and calculate the value of normal reaction. The value of R equals to weight of block as the block does not have any acceleration. Think about the normal reaction acting on the block when the block is placed on the floor of a lift and lift is accelerating. Do you know that a weight measuring machine measures normal reaction that will be exerted by you on the machine? The reading of the machine shows the weight of your body, but why? You can understand this by drawing your free body diagram and calculate normal reaction acted on you. It is the same situation as the block placed on the table. The value of normal reaction on you equals to your weight. You are applying the same magnitude of normal reaction on machine and hence machine measures the force applied by you, that is normal reaction. You can see a man is standing on a weighing machine in a lift. Now the reading of machine depends on the fact that lift is accelerating or not. Three cases can possible. If lift is at rest, then reading of machine is weight of man. If lift is accelerating upward, then reading of machine is greater than his weight. If lift is accelerating downward, then reading of machine is less than his weight. If lift is in free fall, then the machine gives zero weight, and this is the situation of weightlessness. Humans experience their own body weight as a result of this supporting force, which results in a normal force or normal reaction applied to a person by the surface of a supporting object, on which the person is standing or sitting. In the absence of this force, a person would be in free fall, and would experience weightlessness. Humans experience their own body weight as a result of normal reaction applied to a person by the surface of a supporting object, on which the person is standing or sitting. In the absence of this force, a person would be in free fall, and would experience weightlessness. Zero-G is an alternative term for weightlessness and holds for instance in a freely falling lift. Zero-G is subtly different from the complete absence of gravity, something which is impossible due to the presence of gravity everywhere in the universe. A common conception about spacecraft orbiting the Earth is that they are operating in a gravity-free environment. Spacecraft are held in orbit by the gravity of the planet which they are orbiting. The sensation of weightlessness experienced by astronauts is not the result of there being zero gravitational acceleration, as seen from the Earth, but of there being no normal reaction that an astronaut can feel because of the free fall condition. In this session we discussed about gravity, normal reaction and weightlessness on the basis of Newtonian mechanics. In next session we will discuss the application of Newton's second law,